So suppose you are going for a hike on a mountain. You need to pack your bag and you have a bunch of stuff lying around like book, pen, camera, water bottle, etc. Would you pack everything you see? No, right? You would minimize the weight you carry and pack only what's necessary for this hike. In Lasso Regression, we do something similar. We minimize the weight of our model and keep only the most important features. Some features are essential for making accurate predictions. Lasso regression, short for least absolute shrinkage and selection operator, is a regression technique that simplifies a model by adding a unique penalty. So, this is a simple linear regression equation where x1, x2, and so on are the features, and theta 1, theta 2, up to theta n represent the coefficients or weights which symbolize the importance of each feature. And for machine learning models, we have a cost function which is used to measure how well a machine learning model is performing. The cost function for linear regression equation is sum of square residuals, which is represented by this equation where yi is the predicted value and yi hat is the actual value. And this graph represents this SSR. Now, lasso regression introduces a penalty, which is the sum of absolute values of the coefficients multiplied by lambda. This lambda controls how much effect penalty has, and it can vary from 0 to infinity, where 0 means no penalty and it acts like linear regression. So the cost function for lasso regression becomes this. It is the sum of SSR plus penalty term. The first term is the sum of square residuals, which measures how well the model fits the data. The second term is our penalty term, which we just discussed. And lambda controls how strong this whole penalty is. So while training the machine learning model, it will try to reduce the cost function, and while doing so, the penalty term forces some coefficients to be very small, and for large enough lambda, the coefficients of less important features are shrunk to 0, effectively removing them from the model. The parameter lambda plays a critical role in controlling how much regularization is applied to the model. When lambda is close to 0, the penalty term has less impact, and it acts almost like standard linear regression. As lambda increases, the penalty term becomes more influential, and the model will begin to shrink coefficients more aggressively. In the graph, you can see that the actual coefficients represented by the blue line are significantly higher compared to the coefficients obtained using lasso regression. To select the optimal value of lambda, we use cross-validation. I have covered cross-validation in detail in a previous video, and you can find the link in the description. Cross-validation helps ensure that the chosen lambda minimizes error while balancing the risk of overfitting and underfitting. Now let's understand this with an example. Let's say you have a dataset predicting house prices based on multiple features like house size, number of rooms, neighborhood quality, and distance from parks. Some of these features might not contribute significantly to predicting the price, right? Now, let's say after fitting a standard linear regression model without regularization, we get the following coefficients. So, plugging in these values into lasso cost function would result in this equation. And let's say we are using lambda of value 2. Now, the machine learning model's job is to minimize this entire equation. Initially, The coefficients start with some values, like the ones we fitted using standard linear regression model. After fitting this value, we have this equation. But our model will adjust the coefficients and Bayer's term iteratively to reduce the value of this equation. Through this iterative process, the model tries multiple values for the coefficients, gradually moving towards the set of values that minimize the equation. During this process of finding the optimal coefficients, the penalty term's value will also change because it directly depends on the current values of the coefficients, right? Now, let's assume Lasso shrinks the coefficients like this: 0.15, 4.5, 1.5, and distance to park becomes the coefficient for distance to parks becomes 0. Now, house size has shrunk from 2 to 0.15, while distance to park came from 4 to 0. This is because while predicting the values, the difference between actual and predicted values was not influenced much by the distance to parks. And during the minimization of the equation of the cost fraction, distance to parks was reduced to 0 due to the penalty term. Okay. Now, when to use lasso regression? Lasso regression is a great choice when feature selection is important and you want to reduce the complexity of your model by eliminating irrelevant features, simplifying your model. Lasso helps prevent overfitting by imposing a penalty on large coefficients, which can occur when the model fits too closely to the training data. That's all for this video. Thank you for watching, and I'll see you in the next one.